Tito is a product engineered for you to have exactly the audio experience you want. Tune in to what you want to hear and tune out what you don't. Tito provides a lightweight, user-personalized solution for selective noise isolation. The device is snap-on. It attaches to any existing headphone set to create a customized selective noise isolation system. Simply plug the Tito auxiliary cord into the headphone's aux input. It has an ergonomic form factor at 7.8 ounces, sitting atop and around the user's headphones. It has a battery life of 5 hours, sourced from an on-device rechargeable battery. Tito provides selectivity. An adjustable onboard analog filter tunes out audio signals not selected by the user. In parallel, software on the microprocessor performs digital signal processing to further isolate the audio, as well as factor in specially selected audio by the user. These settings are chosen in the companion app in a user-friendly interface and coordinated with the device through low-energy Bluetooth 5.0.
Users can control Tito using our Bluetooth-enabled mobile app. The app is designed to scan filter for our Tito device, and once connected, the user is able to adjust their desired frequency listening range to their liking. As you can see, the user can adjust two cutoffs, high and low, and when the user is finished adjusting to their preferred range, they can simply click the update button, and our backend does the rest. We leverage a Bluetooth socket connection between the Raspberry Pi and our app in order to send the desired frequency tunings to our Raspberry Pi, which is outfitted with our custom Tito Pi app, which forms the central hub for communications between our microphone arrays and our device.
So how does this all work? We take advantage of microphone directionality in order to utilize a microphone array on Tito. In the first model, we established proof of concept with two microphones, one directed out of the left ear and the other directed out of the right. In our final model, we're able to successfully leverage 6 total microphones in our microphone array. Each ear will have a microphone board consisting of 3 microphones, strategically spaced out such that each microphone can pick up a sound in a distinct angular direction, which allows the user to leverage the directionality of the microphones to create their own space, which is an important part of the Tito experience. The signal from each microphone is then fed into an amplifier, and the resultant signal is fed into 2 separate paths, an analog path and a digital path. The analog path consists of programmable bandpass filters, consisting of a cascaded high-pass and low-pass filter. The user can send commands via the app in real time to the filters, which in turn changes the resistant values on the programmable filters and hence changes the cutoff frequency. From the user experience point of view, it's just simply changing the slider on the app, and in real time, the bandpass filters cutoff frequencies are changed. Each microphone also has a programmable resistor such that it can be turned on and off, and this is an important part of allowing the user to control your space by being able to turn on and off individual microphones. The digital path consists of the ADC, which converts the analog signals into digital signals and uses SPI, Serial Peripheral Interface Protocol, to send the signals to the on-device processor, which is the Raspberry Pi that has a custom-built Tito Pi hat on it. Software on the Pi performs digital signal processing to process the data coming in from the microphone array and isolates audio in the direction selected by the user. So the digital path is for our signal processing capabilities on Tito. The companion app sends commands to the Raspberry Pi via Bluetooth to configure which audio signal to isolate. The digital signal processing also involves recognizing special sounds selected by the user to include, for example, emergency alarms or particular person's voice, or it could be at a train stop, the sound of a train. These 2 paths come together on board through an adder and are fed into the user's headphones through an aux connection. All this processing, the entirety of it, occurs in less than 300 nanoseconds, which is a latency undetectable to human ears.
Here are the components inside of a Tito device. We first see that under the lid we have a central hub printed circuit board that connects the other circuit boards to the Raspberry Pi. This PCB sits right on top of the GPIO pins of the Raspberry Pi for easy connection. On each ear there are 3 boards which each contain 1 microphone. This creates the 6 microphone array of our device. The larger central board contains the amplifiers and filters that are controlled by the Raspberry Pi. As you can see, all of these custom PCBs fit inside of our lightweight 3D printed casing. After our first semester successes with the singular microphone on this PCB, we further iterated to include a 6 microphone array as well as the tunable filter in parallel to the digital audio path. So how does this controllable bandpass filter work? We designed a fourth order bandpass filter and a MOSFET push-pull amplifier to drive the low impedance load of the headphones. By sweeping the resistance values of the potentiometer over its full range, we can see that the high-pass filter has a cutoff frequency range from 10 Hz to 10 kHz, and the low-pass filter has a cutoff frequency range from 500 Hz to 20 kHz. Here is the breadboard that was used to test our circuit design. This includes our MEMS microphone, the filter, and the output amp that connects to a pair of headphones through an aux cable. The filter is made of potentiometers, which are variable resistors, as well as capacitors. The variable resistors control the cutoff frequency of the filter, and in this case are controlled by knobs, where in our final product they're controlled by software. The next video will show how effective the filter is in reducing the sound that is outside of the allowed band of the filter.
Alright, welcome to the Tito Labs. We have a 500 Hz waveform coupled with a 5 kHz waveform, and AJ is going to do AJ stuff.
As you can see on the oscilloscope, we have a signal. The resulting signal is a combination of the two waves. As I change the cutoff frequency lower on the low-pass filter, you can see that the resulting waveform becomes more like the 500 Hz signal.
From the hardware, the audio signals are converted from analog to digital and sent via SPI to the computing platforms, where we perform digital signal processing. Since the microphones are directional, it picks up signals in its coverage region stronger than it does signals outside of its coverage region. With multiple microphones, we can obtain different audio views of the same environment. Convert these signals to the frequency domain and we can see the situation a bit clearer. If we only want to hear the audio coming into the right ear, we can modulate the audio from the left ear down to the amplitude at which it exists in the right ear, and then subtract it from the right ear's audio. Now the only audio that remains is the one we want. Let's demonstrate this by generating microphones 1 and 2 of Kyler and Ransford speaking together. Kyler and Ransford have similar voice profiles, so we can test just how good the program is. Say we want to listen to what Kyler has to say, but we want to cancel out Ransford's voice. This is what you would hear through microphones 1 and 2 together without any processing.
So we
Hello
set out to
everyone,
technically
this
solve
is
this
teammate
problem
and
by
we're
utilizing
Tito.
what we've termed to be
Imagine
a
sitting in
Snap-on
a crowded
solution
lecture
approach
hall
for
trying to pay
existing
attention
hardware.
Here's what it sounds like through the dominant microphone input.
So we
Hello
set out to
everyone,
technically
this
solve
is
this
teammate
problem
and
by
we're
utilizing
Tito.
what we've termed to be
Imagine
a
sitting in
Snap-on
a crowded
solution
lecture
approach.
After running both microphones' inputs through the processing function, along with the factor of magnitude difference, we'll manage to isolate the audio we want.
So we set out to technically solve this problem by utilizing what we've termed to be a Snap-on solution approach for existing hardware, which essentially means that we can connect our filter setup to any headset or headphone device with an aux in.
We tested this out with a couple different magnitude differences and found that any factor worked. For fun, we can look at if we separate AJ and Celine's voices.
Considerations where our target
From the
user group,
communication
since
perspective
we
here
are
on the right,
developing
we
this
managed to
our main considerations were our target user group, since we are developing this for focus.
However, we know that even if we design our hardware to pick up this magnitude difference, there will be imperfection. So we experimented to examine what amount of imperfection our ears can tolerate while still having a Tito experience. This is what a 5% factor imperfection sounds like.
Our main considerations were our target user group, since we are
It's pretty close to perfect. At 20%, we start to lightly hear the voice that we wanted to cancel.
our main considerations were our target user group, since we are developing this for focus assist.
40% is what we determined experimentally to be the limit of imperfection that still enables cancellation to a tolerable Tito extent.
Our main considerations were our target user group, since we are developing this for focus assist.
Now let's hear the 40% imperfection with Kyler and Ransford.
So we set out to technically solve this problem by utilizing what we've termed to be a Snap-on solution approach.
As engineers, we are designing Tito to be as robust as possible to imperfect usage circumstances.
The future of Tito is bright. In our ideation phase, one of the key components we wanted to incorporate was the use of machine learning to characterize certain voice profiles. So for example, through the app, you'll be able to record a specific voice sample, and that will be passed into a cloud infrastructure backend to characterize that voice profile and associate it with a specific person. We established proof of concept with this earlier in the semester by working with a large corpus of voice recordings and being able to determine certain characteristics such as gender and nationality from that data set. And now the logical next step would be able to equate that with an actual speaker and use that within our selectivity process on Tito.
With more time, we hope to improve and develop this model so that we can use it on the device to classify speakers speaking at any given time, and in real time be able to modify the filter and DSP according to user configuration. The final product would be something like the user selecting who they want to listen to on the companion app, i.e. listen to just Ransford and just AJ, and then the voice detection and profiling would actually auto-adjust and use more advanced signal processing to selectively isolate that sound according to the voice profile rather than simply direction.
Moving forward, with the Tito device, we would like to implement a dedicated microprocessor to the DSP tasks, which would replace the Raspberry Pi. This, in addition to a more optimized design in the PCB, we should be able to reduce the size of the form factor and increase battery life in our device.
We foresee strategic partnership with existing headphone manufacturers who already have high-quality noise cancellation, but who lack the customizable and selective experience that our Tito device offers. Having a part of the hardware already inside these headsets would provide a direct correlation to a reduction in size and cost of our device, creating an even better experience for the consumer.
And in conclusion, we believe that the entire consumer headphone industry would benefit from creative and innovative sound solutions for its consumers. We believe that Tito is a step in the right direction.
Tune in what you want to hear, tune out what you don't.